Oh, good. So we are up to section 3.4 on quadratic residues. We've been looking at kth power residues for any integer k, 2 or greater. A quadratic residue is a tooth power residue, a square. So p is always going to be an odd prime number. And a, an integer not divisible by p. So we say a is a quadratic residue mod p if there exists an integer x such that x squared is congruent to a mod p. So a quadratic residue is a number that has a square root mod p. And if this congruence has no solution, then A is called a quadratic non-residue. Mod p. So every integer relatively prime to p is either a quadratic residue or a quadratic non-residue. And we define a function called the Legendre symbol, after a French mathematician Legendre, a over p with parentheses around it. And this is defined as follows. This is equal to 1 if a and p are relatively prime and a is a quadratic residue. Mod p, minus 1 if a and p are relatively prime and a is a quadratic non-residue, and 0 if p divides a. So for example, suppose we take p equal 5. So 0 over 5, that's the Legendre symbol, is 0 because 5 divides 0. 1 over 5 is 1 because 1 squared is congruent to 1 mod 5. So 1 has a square root. Similarly, the Legendre symbol 4 over 5 is 1 because 2 squared is congruent to 4 mod 5. But 2 over 5 is minus 1 because x squared is not congruent to 2 mod 5, no matter what x you pick. And similarly, the Legendre symbol 3 over 5 is minus 1 because there's no x such that x squared is congruent to 3 mod 5. So this gives the value of the Legendre symbol for p equal 5 for 0, 1, 2, 3, and 4. And the Legendre symbol only depends on the congruence class of A.
Professor,
Yes,
I'm sorry, but you put 1 when you put 4/5, and it's supposed to be 4, no?
I'm sorry.
In 4/5, right? It's not 4, you put 1.
Correct.
It is 1 or 4.
4/5 equals 1.
Oh. Okay. I'm asking because you put 2 squared equal to 4. Okay.
Right,
Never mind.
exactly. So this means to say 4/5 is 1 means that 4 is a quadratic residue. That means you can solve the congruence, x squared congruent to 4 mod 5. And here's the solution, x equal to 2.
Okay, got it. Thank you.
Okay. We can also observe that if A is congruent to B mod P, then A over P equals B over P. So the Legendre symbol only depends on the congruence class of the numerator, because x squared is congruent to A mod P. A is congruent to B if and only if x squared is congruent to B mod P. And A is congruent to 0 mod P if and only if B is congruent to 0 mod P. So the Legendre symbol is really a function on congruence classes. It only depends on the congruence class of A mod P. Also, we make some other observations. For a prime, x squared is congruent to 1 mod P if and only if x is congruent to either +1 or -1 mod P. Because the integers mod P form a field, a quadratic equation has at most 2 roots. This is a quadratic equation mod P, and it has exactly 2 roots, so there can't be any more. Let's make another observation. P is an odd prime if we choose 2 numbers, epsilon and epsilon prime, from the set -1, 0, and 1. So these numbers are either plus or minus 1 or 0. Then if epsilon is congruent to epsilon prime mod P, that means P divides epsilon minus epsilon prime. And epsilon minus epsilon prime is at most 2, right? The difference between 2 numbers in this set is at most 2. So the only way a prime P, which is at least 3, divides a number which is at most 2 is if the number is 0. So epsilon equals epsilon prime. So this is just a little bit of baby arithmetic. The difference between 2 numbers, -1, 0, and 1, is either 0, plus or minus 1, plus or minus 2. The only one of those integers divisible by an odd prime P is 0. So we have this statement. And it follows that if the Legendre symbol is congruent to epsilon mod P for some epsilon, which is either -1, 0, or 1, then P, and this A over P, the Legendre symbol, only takes on values -1, 0, or 1. So if A over P is congruent to epsilon mod P, then A over P equals epsilon. Okay, so now we can prove our first theorem about quadratic residues. And it's quadratic residues that are really the goal of this course, what we study for the rest of the course, basically. It's the most important part of elementary number theory. So this is theorem 312 in the text, which says that for every odd prime p and every integer a, the Legendre symbol a over p is congruent to a to the power p minus 1 over 2 mod p. Okay, so the general question we want to solve is, given a prime p, find the quadratic residues. How do you know if a given integer is a quadratic residue? And the quadratic residue is, in a sense, determined by the Legendre symbol. A is a quadratic residue if and only if this is +1. And this says that whatever this number is congruent to a to the p minus 1 over 2. So there's one sort of trivial case. If p divides a, then a over p is 0, and a to the p minus 1 over 2, p minus 1 over 2 is an integer, right? P is odd, so p minus 1 over 2 is an integer. So this is a to an integer, a positive integer, and a divides p. So this is divisible by p. So this is congruent. They're both congruent to 0 mod p. So this statement is true if p divides a. Right, so that's the first case. If p does not divide a, then by the Euler-Fermat theorem, a to the p minus 1 is congruent to 1 mod p. And a to the p minus 1 is a to the p minus 1 over 2 squared, just by the rules for exponents. P minus 1 over 2 times 2 is p minus 1. So this number squared is 1. So a to the p minus 1 over 2 is plus or minus 1 mod p. Of course, there are only two numbers whose squares are 1 mod p, plus 1 and minus 1. But we had already proved a theorem. This was theorem 311. So by theorem 311, A is a quadratic residue mod p if and only if a to the p minus 1 over 2 is congruent to 1 mod p. So that was the theorem we proved on Monday. So a over p is 1. That means a is a quadratic residue if and only if a to the p minus 1 over 2 is congruent to 1 mod p. And what is the alternative? A is not a quadratic residue So this symbol is -1 if and only if a to the p minus 1 over 2 is congruent to -1 mod p. So in both cases, a to the p minus 1 over 2 is equal to the Legendre symbol a over p, right? If this is 1, this is 1. If this is -1, this is -1. So that proves our theorem. Let's just look at an example of this. Let me just repeat this here so I have it at the top of the page. A over p equals 1 if and only if a to the p minus 1 over 2 is congruent to 1 mod p. So, for example, suppose I take a equal 3 and p equal to 11. So I need to compute 3 to the power 11 minus 1 over 2. That's 3 to the 5th. What is 3 to the 5th? Well, what is 3 to the 5th? Mod 11. So 3 to the 5th, we have 3, 9, 27, 81, 243. And if you divide 243 by 11, you get 1 mod 11. So 3 is a quadratic residue. 3 over 11 is equal to +1. Because 3 to the 11 minus 1 over 2 is congruent to 1 mod 11. So 3 is a quadratic residue. This doesn't tell us how to find the square root, but it does tell us that the equation x squared congruent to 3 mod 11 has a solution. Suppose we take a equal to 3 and p equal to 13. So we have to calculate 3 to the 13 minus 1 over 2. That's 3 to the 6th mod 13. 3 to the 6th is 729. If we divide 13 into 729, 65, 79, 6 times 13 is 78. We get a remainder of 1. This is congruent to 1 mod 13. So therefore, the Legendre symbol 3 over 13 equals 1. So x squared congruent to 3 mod 13 has a solution. 3 is a quadratic residue mod 13. Let's keep looking at 3. Let's try the next prime, 17. So we want to look at the congruence 3 to the 17 minus 1 over 2. 17 minus 1 is 16. This is 3 to the 8th. And we want to know what is 3 to the 8th mod 17. We know it's +1 or -1. Let's see, which one is it going to be? Oops, excuse me 1 second. Yeah, so we have to calculate 3 to the 8th mod 17. So that's just doing some arithmetic. 3 to the 4th is 81. Let's see, 17, 34, 68. Is that right? 81 is the same, I think, as minus 4 mod 17. So 3 to the 8th, which is 3 to the 4th squared, is minus 4 squared, is 16, which is minus 1 mod 17. So 3 to the p minus 1 over 2 is minus 1 minus 17. So 3 is not a quadratic residue. The Legendre symbol is minus 1, which means x squared congruent to 17, congruent to 3 mod 17 has no solution. So x squared is not congruent to 13 for all x. Okay. So the Legendre symbol tells us it's just saying yes or no, is A a quadratic residue mod P or not? And this gives one criterion: if A to the P minus 1 over 2, that's either plus or minus 1, and it's 1 if and only if A is a quadratic residue. So that's very important. Okay, so here is, we have several theorems to prove today. This is theorem 313. It says something about the multiplicativity of the Legendre symbol. So again, P is always an odd prime. A and B are integers, and AB over P equals A over P times B over P. That's the multiplicativity of this function. We think of P as being fixed, and this is a function of the numerator of the fraction. So the first case is simple. If P divides A or B, or both, then P divides AB, and so AB over P is 0, and you have A over P and B over P. At least one of these two is 0, so the product is 0. So if P divides A or B, this statement is true. So that's the first case. And the second case is if P does not divide either one, which means it doesn't divide the product, then AB over P, so we know this is all mod P, is congruent to AB to the P minus 1 over 2, which is the same as A to the P minus 1 over 2 times B to the P minus 1 over 2. And this is congruent to A over P, and this is congruent to B over P. And that's the whole proof. And this, as a corollary of this, the Legendre symbol is completely determined. You can calculate it by knowing minus 1 over P, because A can be positive or negative, 2 over P, and Q over P for all odd primes Q, right? Let's see, why is that? So for example, suppose A is equal to minus 120. What is 120? We can factor it. It's minus 1. 120 is 5 times 24, 2 cubed, 3 to the first power, 5 to the first power. This is minus 120. So minus 120 for any prime p. So suppose p is some prime not 2, 3, or 5, some prime greater than or equal to 7, minus 120 over p, that's minus 1, 2 cubed, 3 to the first power, 5 to the first power over p. This is minus 1 over p, 2 cubed over p, 3 over p, 5 over p, just using the multiplicativity. And 2 cubed over p, this is minus 1 over p, 2 over p cubed, 3 over p, 5 over p. So if you have any number a, once you factor it into a product of prime powers, you can calculate the Legendre symbol for that number a. And it only depends on the Legendre symbol, where the numerators are either minus 1, plus 2, or some odd prime cube. Now, it turns out we can quickly decide when minus 1 over p is plus 1 or minus 1. Now, this is really interesting because minus 1 over p is 1 if x squared congruent to minus 1 mod p has a solution, or x squared plus 1 congruent to 0 mod p. You know, this equation in the integers has no solution. In the reals has no solution. In the complex numbers it does. But when you're looking at this congruence mod p, it's not so obvious what the answer is. So, but let's use our theorem. So, in fact, I'll state this as our next theorem. Minus 1 over p is 1 if p is congruent to 1 mod 4, and minus 1 if p is congruent to 3 mod 4. Right? You take an odd prime and you divide it by 4, the remainder is either 1 or 3. Minus 1 has a square root mod p if p is 1 mod 4, and it doesn't have a square root if p is 3 mod 4. And what is the proof? Well, the proof is pretty simple. Minus 1 over p is congruent to minus 1 to the p minus 1 over 2 mod p. Let's see. If p is congruent to 1 mod 4, that means p is 4k plus 1. That means p minus 1 is 4k. P minus 1 over 2 is 4k over 2 is 2k. That's even. So if p is congruent to 1 mod 4, this is minus 1 to an even number, which is plus 1. If p is congruent to 1 mod 4. If p is congruent to 3 mod 4, that means p is 4k plus 3 for some k. So p minus 1 is 4k plus 2. Divide by 2, we get 2k plus 1, which is an odd number. So in this case, minus 1 over p, this is minus 1 to the p minus 1 over 2. This is minus 1 to some odd power. This is minus 1 mod p. So minus 1 over p is minus 1. So from our criterion about a to the p minus 1 over 2, we've completely solved the problem of knowing when minus 1 has a square root mod p. All right, let's take an example. Suppose I take p equal to 17. 17 is congruent to 1 mod 4. So that means that minus 1 over 17 is 1, which means somewhere there exists an integer x such that x squared is congruent to minus 1 mod 17. It turns out it's easy to find such a number. You can choose x congruent to 4 or x congruent to minus 4, which is 13 mod 17. So you have a solution. What about p equal 19? 19 is 3 mod 4. So minus 1 over 19 is minus 1. That means x squared is never congruent to minus 1 mod 19. So you don't have to look for a solution. There isn't any. No matter, you can square all the numbers from 1 to 18. Not one of them will be congruent to minus 1 mod 19. So that's really a useful result. Remember, I said that this Legendre symbol is completely determined if you know its values for minus 1, 2, and the odd primes. So I just found a simple formula for knowing when minus 1 is a quadratic residue mod p. What about for 2? That's also an important special case. And there's a theorem that I'll prove in a moment, but it needs a preliminary result, which also tells us when 2 over p is 1. So 2 is a quadratic residue. So p is an odd prime. So 2 never divides p. If p is congruent to plus or minus 1 mod 8, and it's minus 1 if p is congruent to plus or minus 3 mod 8, right? So this completely determines the value of the Legendre symbol for 2. See, what do these congruence mean? P is an odd prime. So p is equal to 8 if you divide it by 8 plus a remainder, and the remainder is odd. 1, 3, 5, or 7. But 5 is the same as minus 3 mod 8. And 7 is the same as minus 1 mod 8. So this is just the concise way of writing down all the cases. So what's an example? Let's look at a couple of examples. So 2 over p is 1 if p is congruent to plus or minus 1 mod 8, and minus 1 if p is congruent to plus or minus 3 mod 8. So suppose I take p equal to 11. So 11 is congruent to 3 mod 8. So that means that x squared is never congruent to 2 mod the prime 11 for all integers x. There's no solution of this congruence. What about 17? 17 is congruent to 1 mod 8. So this means there exists an x such that x squared is congruent to 2 mod 17. this doesn't tell us how to find the square root of 2 mod 17. It tells us that there is one, which means if you start squaring the integers mod 17, you'll have to get a solution. Let's just do it the hard way. 1 squared is congruent to 1. I want to get 2 on this side. 2 squared is congruent to 4. 3 squared is congruent to 9. 4 squared is 16, congruent to 16. 5 squared is 25, that's congruent to 8. 6 squared is 36. 2 times 17 is 34. So this is congruent to 2 mod 17. So I can take x equal to 6, and I could also take x equal to minus 6, which mod 17 is the same as 11. Right? So 2 is a quadratic residue mod 17. 2 is not a quadratic residue mod 11. Okay. Suppose we take p equal to 19. See, 19 is congruent to 3 mod 8. That means x squared congruent to 2 mod 19 never has a solution because p is a prime congruent to 3 mod 8. 19 is a prime congruent to 3 mod 8. So 2 is not a quadratic residue. What about p equal 23? Let's see, 23 is 16 plus 17. This is congruent to 7 or minus 1 mod 8. So x squared congruent to 23, sorry, x squared congruent to 2 mod 23 will have a solution. So just so I can share the fun, why don't you spend a minute or two and look for a solution to this congruence? Find a number x where x squared is congruent to 2 mod 23. I'll give you a hint. This one is really easy, easier than this. Yeah, x equal 5, because 5 squared is 25, is congruent to 2 mod 23. 25 minus 2 is 23. So a solution is x equal 5, any x congruent to 5, or any x congruent to minus 5, which is the same as 18 mod 23. Let's see, why 18? 18 squared, what is 18 squared? Anyone know quickly?
Leo. 324, Professor.
324. So 18 squared minus 2 is 324 minus 2 is 322. And if we divide 23 into 322, get 92 for, it goes evenly. This is exactly 14 times 23. So 18 squared is congruent to 2 mod 23. Right? Okay. Now, it was easy to prove for which primes minus 1 was a quadratic residue. It's much more complicated to find out for which primes 2 is a quadratic residue. And we need to use the following result and definition. So P is an odd prime. So there are p minus 1, which is some even number, distinct, non-zero congruence classes modulo p. So if they're p minus 1 congruence classes, half of them would be p minus 1 over 2. So let S be a set of half this number, p minus 1 over 2 integers, such that S together with the set minus S. Minus S just means the set of all numbers, the negatives of all the elements of S. So here I have p minus 1 over 2 numbers. Here I have p minus 1 over 2 numbers. If these are distinct, I have altogether p minus 1 numbers. And I want to take a set S such that of p minus 1 over 2 numbers, such that the set and their negatives is a reduced set of residues modulo p. So here's an example. Suppose I take p equals 7. So p minus 1 over 2, 7 minus 1 over 2, or 6 over 2 is 3. Suppose I just take S to be the set 1, 2, 3. Then minus S is the set minus 1, minus 2, minus 3, just the negatives of these. And S union minus S is the set 1, 2, 3, minus 1, minus 2, minus 3. And this is a reduced set of residues mod 7, because 1 is congruent to 1 mod 7, 2 is congruent to 2, 3 is congruent to 3, 4 is congruent to minus 3, 5 is congruent to minus 2, and 6 is congruent to minus 1 mod 7. So every congruence class relatively prime to 7 is congruent to one of the 6 numbers in this set. So this is an example of a set with these properties, and such a set is called a Gaussian set. So a Gaussian set mod p is a set of p minus 1 over 2 integers such that S union minus S gives you one representative from every congruence class relatively prime to p. Okay, so that's a Gaussian set. And Gauss, 200 years ago, proved the following result. It's called Gauss's lemma, but it's a very important theorem. So it says the following. So we take p, an odd prime, and an integer a, which is not divisible by p. That is, a and p are relatively prime. Let S be a Gaussian set mod p. So this consists of half of the non-zero residues mod p, and the other half are the negatives of the elements of S. So for every element S in S, there exist unique integers U sub A of S in the set S and epsilon sub A of S, which is either +1 or -1, such that AS is congruent to epsilon sub A of S, U sub A of S, mod P. So the notation here is a little bit complicated, but what this really says is completely immediate from the definition. A is relatively prime to P. Every element S in the set capital S is relatively prime to P. So this number is relatively prime to P. So it's equal to plus or minus some element of S. So the plus or minus is this epsilon, is +1 or -1, and U sub A of S is the element of S. So this statement is instantaneous from the definition of a Gaussian set. And here is the important statement. Moreover, the Legendre symbol A over B, P, which tells you whether or not A is a quadratic residue mod P, is the product over all the S and S's of these plus or minus 1 signs, epsilon sub A of S. So each of these numbers is 1 or -1. So this is equal to either +1 or -1, right? You multiply plus or minus 1, you get plus or -1. So this is equal to -1. Well, how many -1s are there? Let's say this is -1 to the M, where M is the number of S in S such that this is -1. Epsilon sub A of S is -1. So this is the statement that we have to prove. So let's look at the proof. This is probably the most subtle thing we've had to prove so far in this course. Suppose I take two elements, S prime and S and S prime in the set S. So I have for each of the elements S and S prime, U sub A of S and U sub A of S prime. If U sub A of S equals U sub A of S prime, what does that mean? It means that AS prime, which is congruent to epsilon sub A of S prime, U sub A of S prime. But this is going to be U sub A of S is equal to U sub A of S prime. So this is epsilon sub A of S prime, U sub A of S. This is all mod P. And the epsilon sub A of S, these are plus or minus 1s. So this is the same as epsilon sub A of S prime, epsilon sub A of S times epsilon sub A of S times U sub A of S. I just put this in the middle, but this is either 1 times 1 or -1 times -1. It's 1 in both cases. And this is AS is equal to AS. So this is plus or minus 1. So this is congruent to plus or minus 1 AS mod P. And A and P are relatively prime, so I can divide by the A's. I get S prime is congruent to plus or minus S mod P. But S and S prime are in the set S. And if S is in the set, capital S minus S is not. So this can't be equal to a minus sign. So that means that S prime has to equal S, right? If S prime is congruent to minus S mod P, then there'd be something in minus S, which was in S, and we wouldn't have a reduced set of residues mod P. Right? That's an important point that you need to think about a little bit. So if U sub A of S equals U sub A of S prime, S equals S prime. Another way of saying this is the function, the map, U sub A from S to S is a permutation of S. This is a one-to-one function of these finite sets. So every element in S is the image of something in S under this map. So that just means that if you take the product of all S in S of S, that's the same as the product of all S in S U sub A of S. So therefore, if I take A to the P minus 1 over 2 times the product of all S in S of this element little s, the cardinality of the set S is P minus 1 over 2. So this is the same as the product over all S and S of AS mod P. Everything is mod P. And AS we can write as plus or minus 1 U sub A of S. This is the product for all S in S, use epsilon sub A of S, U sub A of S. So this is the product for all S in S, epsilon sub A of S, product for all S in S, U sub A of S, which is the same as this. Mod P. So I have A to the P minus 1 over 2 times this is congruent to this product times this product. And all of these four numbers are relatively prime to P, so this cancels. So I get A to the P minus 1 over 2 is congruent to the product epsilon sub A of S for all S in S which is minus 1 to some m. M is the number of minus ones here, mod P. And this is the Legendre symbol A over P. A over P is congruent to this. So this number, which is plus or minus 1, is congruent to this, which is plus or minus 1. The difference is divisible by P. So A over P equals minus 1 to the m. So this is a proof that I don't think you can understand when you just see it in front of you the first time. It's something that takes some time at home to work through carefully and think about and justify every single detail. But let's look at an application of this. So an application of Gauss's lemma. Suppose I take P to be the prime 11, and I take S, so P minus 1/2 is 5. Suppose I take S to be the set 2, 4, 6, 8, 10. Then minus S is the set -2, -4, -6, -8, -10. And these numbers are congruent mod 11 to the numbers, let's see, -10 minus 11 is 1, -8 is 3, -6 is 5, -4 is 7, and -2 is 9. So S is the numbers 2, 4, 6, 8, and 10. Minus S represents the congruence classes 1, 3, 5, 7, and 9. So S union minus S, which is plus or minus 2, plus or minus 4, plus or minus 6, plus or minus 8, plus or minus 10, is a reduced set of residues modulo 11. Every non-zero number is congruent to exactly one of these. Suppose I take the number A equal to 3. And I want to use Gauss's lemma to compute 3 over 11. That is, I want to be able to figure out what is the value of this Legendre symbol. So in Gauss's lemma, I have to compute A times S. That's 3S. This is going to be congruent to epsilon sub 3 of S, U sub 3 of S, mod 11, where epsilon sub 3 of S is plus or minus 1, and U sub 3 of S is in S. So I have to compute this for each S. There are 5 of them. So S times 2, sorry, 3 times 2, I have to do this for 2, 4, 6, 8, and 10. I have to compute 3 times 2, 3 times 4, 3 times 6, 3 times 8, and 3 times 10. Mod 11. 3 times 2 is 6, which is 1 times 6. Mod 11. So epsilon sub 3 of 2 is plus 1, and epsilon sub 3 of, and U sub 3 of 2 is 6. 3 times 4 is 12. 12 is the same as minus 10, mod 11, right? Because 12 is the same as 1 is the same as minus 10. 10's in my set S. This is minus 1 times 10. So epsilon sub 3 of 4, that's a minus sign, that's minus 1. And U sub 3 of 4 is 10. 3 times 6 is 18. 18 is 7 mod 11, which is the same as minus 4, which is minus 1 times 4 mod 11. So epsilon sub 3 of 6 is minus 1, and U sub 3 of 6 is 4. 3 times 8 is 24. 24 is 2 mod 11. That's plus 1 times 2. So epsilon sub 3 of 8 is plus 1, and U sub 3 of 8 is 2. And 3 times 10 is 30. Mod 11, 30 is 8. 1 times 8. So epsilon sub 3 of 8 is plus 1, and U sub 3 of 8 is 8. So here are my epsilons, and m is the number of minus ones.
Sir,
So m,
Professor,
yes,
the question. The last one should it be E sub 3 of 10 equals 1 and U sub 3 of 10 equals 8? No?
so epsilon sub 3 of 8 is 1, and u sub 3, sorry, u sub 3 of 10. 10 is
10,
the
yeah.
number there. Thank you.
10, yeah.
U sub, yeah. U sub 3 of 10 is 1, and u sub 3, epsilon sub 3 of 10 is 1, u sub 3 of 10 is 8. M is the number of minus ones. There are two of them. So the Legendre symbol 3 over 11 is minus 1 to the m, which is plus 1. So 3 is a quadratic residue mod 11. Right? This is not in the long run the best way to determine whether or not 3 is a quadratic residue, but this shows you this is an application of Gauss's lemma. Right? Okay, now I want to use Gauss's lemma to prove the theorem about quadratic residue, whether of determining the primes for which 2 is a quadratic residue. So what we're going to do is use Gauss's lemma to determine the primes P for which 2 over P is equal to 1. For what primes is 2 a quadratic residue? And okay, so we take an odd prime P, choose the Gaussian set S to be just the first P minus 1 over 2 integers. So for each S in S, we're going to write 2S is some epsilon sub 2 of S, U sub 2 of S. With plus or minus 1 times an element of S. And 2 over P will be minus 1 to the number of minus 1s that occur here. So if we look at the set of numbers 2 times S, where S is in S, we're just multiplying each of these numbers by 2. So we get 2, 4, 6, 8, and so forth, up to P minus 1. These are the numbers 2 times S. So for these numbers in the set 2S, what can we say? If 2S is between 1 and P minus 1 over 2, then 2S, which is epsilon sub 2 of S, U sub 2 of S, is just going to be 1. That's what epsilon sub 2 of S will be. And U2 of S will be 2S, because 2S is an even number up to P minus 1 over 2. So if 2s is between 1 and p minus 1 over 2, it's one of these integers, and 2s is 1 times epsilon 2s. So this means that in this case, epsilon sub 2 of s is equal to plus 1. And the alternative case is if 2s is bigger than p minus 1 over 2, so it's at least 1 bigger, so it's at least p plus 1 over 2 and p minus 1. Let's see. So let's see, let me just do a little bit of arithmetic. P minus 2s is greater than or equal to 1. And p minus 2s let me just write this out. So 2s less than or equal to p minus 1 means that 1 is less than or equal to p minus 2s. And p is equal to p minus 1 over 2 plus p plus 1 over 2, right? You add them up, you get p minus 2s. And p plus 1 over 2 minus 2s is less than or equal to 0. I just associated this differently. P plus 1 over 2 minus 2s is less than or equal to 0. So this is less than or equal to p minus 1 over 2. So p minus 2s is a number between 1 and p minus 1 over 2. So p minus 2s is a number in the set S. So let's see. I want to write 2s as plus or minus 1 times something in S. So 2s is equal to let's say 2s is congruent to p minus 2s, right? Because p minus p is 0. So this is the same as minus p minus 2s mod p, because this is 0. Aha! Minus 1 times p minus 2s. So epsilon sub 2 of s is equal to minus 1, and u sub 2 of s is p minus 2s, but in this case, epsilon sub 2 of s is minus 1. So that says what? I have this Gaussian set, the integers from 1 to p minus 1 over 2. I want to use Gauss's lemma, so I have to write 2s as plus or minus an element of s for every element little s in the set big S. That is, for each value of s from 1 to p minus 1 over 2. So there are two cases. If 2s is between 1 and p minus 1 over 2, 2s is already a number in the set S, so this is just 1 times 2s. epsilon sub 2 of s is equal to 1 if 2s is between 1 and p minus 1 over 2. But if 2s is between p plus 1 over 2 and p minus 1, epsilon sub 2 of s is minus 1. So what we have is epsilon sub 2 of s equals minus 1 if p plus 1 over 2 is less than or equal to 2s is less than or equal to p minus 1. So how many s satisfy this condition? Right? The number of such s is m, and 2 over p is minus 1 to the m. M is the number of s that satisfy this condition. So an odd prime p is always congruent to 1, 3, 5, or 7 mod 8. So we have to consider 4 cases. P congruent to 1 mod 8. So P is a number of the form 8K plus 1. So P plus 1 over 2 is 8K plus 1 over 2 is 4K plus 1. And P minus 1 is 8K. So we want to count the number of S such that 4K plus 1, that's P plus 1 over 2, is less than or equal to 2S, is less than or equal to 8K. Divide by 2, S less than or equal to 4K, greater than or equal to 2K plus a half. But S is an integer, so if it's greater than or equal to 2K plus a half, it's greater than or equal to 2K plus 1. And how many integers S are there from 2K plus 1 up to 4K? That number is M. M equals 4K minus 2K is 2K is even. So if P is congruent to 1 mod 8, then 2 over P, the Legendre symbol, is minus 1 to this even power is plus 1. So if P is congruent to 1 mod 8, P is a quadratic residue mod 2. Right? There are 4 cases. Let me just do the next case. The analysis for all of them is the same, and I can do more on Monday if it's in, if you wish.
Professor, real quick.
Yeah, go ahead.
How'd you go from half to plus 1?
Oh, because S is an integer.
Okay, understood. Gotcha.
So if it's bigger than 2K plus a half, it has to be greater than or equal to 2K plus 1. That's like the next integer.
Roger that.
Okay, suppose P is congruent to 3 mod 8. So P is an integer of the form 8K plus 3. So P minus 1 over 2 is 8K plus 2 over 2, or 4K plus 1. And 2S is going to be between 4K plus 1 and P minus 1, which is 8K plus 2. Which means S is an integer divided by 2, 4K plus 1, 2K plus a half. Again, if S is greater than or equal to 2K plus a half, it's greater than or equal to 2K plus 1, less than or equal to S, less than or equal to 4K plus 1. How many integers are in this set? M is equal to 4K plus 1 minus the integers from 1 to 2K. So I get 4K plus 1 minus 2K. That's 2K plus 1. That's an odd number. So if P is congruent to 3 mod 8, 2 choose P, not 2 choose P. Legendre symbol 2 over P is minus 1 to this odd number, which is minus 1. Actually, since I'm doing it, I might as well just do all the cases. Suppose P is congruent to 5 mod 8. So P is 8K plus 5. So P minus 1 over 2 is 8K plus 4 over 2, which is 4K plus 2, less than or equal to 2S, less than or equal to P minus 1, which is 8K plus 4. So if I divide by 2, 2K plus 1 less than or equal to S, less than or equal to 4K plus 2. Right? If P is 8K plus 5, P minus 1 is 8K plus 4 divided by 2 is 4K plus 2. P minus 1 is 8K plus 4. Dividing this by 2, I get 2K plus 1 less than or equal to S, less than or equal to 4K plus 2. So M is the number of integers in this interval. That's 4K plus 2 let's see. Something doesn't look exactly right here. Let me just go back to when I was proving my theorem. So I had epsilon 2s is the number of integers where 2s is between P plus 1 over 2 and P minus 1. Okay. So this is supposed to be P plus 1 over 2. So this is 8K plus 4 over 2, which is 4K plus 2. Let me just do it. So here I have, it's the number of S such that 2S is between P plus 1 over 2 and P minus 1, which is the same as S between P minus 1 over 2 and P plus 1 over 4. That maybe is the easier inequality to use. So let me let me just cross this out and do these same cases again. So 2 over p is -1 to the m, where m is equal to the number of integers s, such that p plus 1 over 4 less than or equal to s less than or equal to p minus 1 over 2. So let me just run through the four cases again. P congruent to 1 mod 8. So P is 8K plus 1. So P plus 1 over 4 is 8K plus 2 over 4 is 2K plus a half. I want the number of integers S greater than or equal to 2K plus a half and less than or equal to P minus 1 over 2. That's 8K over 2, which is 4K. So this is the same as S between 4K and 2K plus 1. And M is the number of such S, 4K minus 2K, which is 2K, which is even. So we get a plus 1. 2 over P is plus 1 if P is congruent to 1 mod 8. If P is congruent to 3 mod 8, so P is 8K plus 3. So P plus 1 over 4 is 8K plus 4 over 4 is 2K plus 1, less than or equal to S, less than or equal to P minus 1 over 2. That's 8K plus 2 over 2, which is 4K plus 1. So M is equal to 4K plus 1 minus 2K, which is 2K plus 1, which is odd. So for primes that are congruent to 3 mod 8, 2 over P is minus 1. If P is congruent to 5 mod 8, P is 8K plus 5. So P plus 1 over 4 is 8K plus 6 over 4 is 2K plus 3 halves, less than or equal to S, less than or equal to P minus 1 over 2, which is 4K plus 2. If S is greater than or equal to 2K plus a half, S is an integer, so it's greater than or equal to 2K plus 2, less than or equal to 4K plus 2. So M is 4K plus 2 minus 2K plus 1, which is 2K plus 1, which is odd. And let me see if I can squeeze in the last calculation right here. If P is congruent to 7 mod 8, P is 8K plus 7. So P plus 1 over 4 is 8K plus 8 over 4, which is 2K plus 2, less than or equal to S, less than or equal to P minus 1 over 2, which is 8K plus 6 over 2, which is 4K plus 3. So I'm looking at the number of S is 4K plus 3 minus 2K plus 1 is 2K plus 2, which is even. So in this case, if P is 7 mod 8, 2 is a quadratic residue. Okay, wow. A little more interesting, I think. So there is a great deal here to think about and work through, and that's one of the reasons why we had just a review class on Monday, and next Monday, again, it's just to review all this, and on Wednesday of next week, we will prove one of the great results in mathematics, which is the quadratic reciprocity law. We have all the ingredients right now. But in any case, their office hours tomorrow, and I think I'll post one on Friday also if you have questions. But Monday is also just a review day. It's just to go over this material. Okay. Any questions before we stop? Okay. All right. Thank you all. Next lecture is on Monday, and if you have questions.
Professor,
Yeah.
sorry. If we wanted to look over this, is there any material online that we could like use?
Well, I'm not sure what you mean. I mean, there's a textbook.
Yeah, I know
lecture
it's
is
your
online.
textbook, but
But
like,
there are, so online, there are probably 100 number theory books or lecture notes that you can see easily. It's just a matter of finding something, you can Google quadratic residues and you will get, I would suspect, 100 different expositions of this material.
okay, so there's not one that you would like recommend you specifically, like a specific one.
No, but what I will do is I will look online myself, and if I find anything that seems particularly valuable, I will either email you the link or just post it on Blackboard.
Gotcha, thank you.
Okay. But this is significantly harder than anything we've done so far in the course. I mean, this proving quadratic reciprocity is a very important piece of mathematics. But it's not easy, which is why it takes the whole semester to build up to it. Any other questions? Okay, thank you all. Have a good weekend.
Have a good weekend too, Professor.